Hello once again, this is presentation 7.4. The topic is confidence intervals, and we want to acknowledge the development team of Brad, Spencer, and Amanda. To illustrate our theory, we're choosing an example here of the birth weight of newborn pups, say in the north. We want to find an estimate of the population mean. So we take a sample of 36 newborn pups, and we know the sigma, standard deviation, 9.0 pounds. Mu is unknown, we're trying to estimate it. So we're looking at the population distribution. See it coming on the screen here now. The population distribution has an unknown mean, sigma is 9, and a confidence interval dictated by a z-score plus or minus 1.96 times the standard deviation gives rise to the notion that 95% of the x values, the single values, fall within plus or minus 17.64 units of the population mean. Now we're going to look at the distribution of sample means based on equal 36, and you know that those sample means will cluster tightly about the population mean, which is unknown. And furthermore, we know that the standard deviation in these x bars is given by sigma, it's up here, divided by square root of n, which turns out to be 9 over square root 36, or 1.5, and that is the 68% region about the center. And we're looking at now a 95% confidence interval about the mean. Z-score is plus or minus 1.96 times your standard error, and that's coming on the screen here, gives rise to this notion of this interval 95% confident that 95% of the x bars will fall within plus or minus 2.94 units of the population mean. And this number is called the 95% margin of error, which is 1.96 times your standard error. It tells us how close we are to the population mean with 95% reliability. Now we've just gone to another screen here. We basically replicated the previous screen. We have a margin of error of plus or minus 2.94. And you see that coming on the screen here now, which represents a 95% confidence interval about the mean. And we now are going to look at several of the x bars. We're saying that 95% of those x bars will fall between these two red lines. And we're denoting these by these red dots. These are x bars coming on the screen. And we're going to show you one of them, possibly. 19 out of 20 will fall between these two red lines. One on average will fall outside. And now if we take each of these sample means, denoted by the red dots, add and subtract this yellow arrows up here, we get what's called a confidence interval. So here's one, x1 bar plus or minus your margin of error, and we're just adding, subtracting these yellow arrows, if you wish, and we get what's called confidence intervals. If you examine these, 19 out of 20 of those confidence intervals will capture that blue line, which represents the population mean. One on average will fail to capture that, and that represents the 1 in 20 or 5% chance of actually missing out on finding the true population mean. And we have now, if we do know an x bar, 67.8, then we imagine one of these intervals to represent x bar of 67.8, add and subtract the 2.94, giving us an interval of 64.86, 70.74, which represents one of these intervals. And we can be 95% confident that the interval will contain the population mean mu, because 95% of all such intervals will capture mu. If the wildlife biologists have data to back up the fact that the mean birth weight in the past was 74.8, what does this result suggest? It suggests the birth weight has dropped significantly below 74.8 pounds. And the general formula for the confidence interval is given by your estimate plus or minus your margin of error, and is given by the z-score here. Well, that's the end of presentation 7.4. We ask that you review it once again, take notes, and go on to section presentation 7.5.